All right, so we will give everybody a chance to get in. And yes, thank you all for signing in the chat. Please remember to do that. All right, well, looks like this will be it for today. All right. So last time, or the last two times, I guess, we've been talking about transformations. So we take a basic, what's called parent graph, and we manipulate it into something new. So we talked about translations, which is just moving something around, but not changing it the way it really looks, just more changing where it is. And then we recently got into doing reflections. So we had talked about and finished talking about two basic kinds of reflections over the x-axis and the y-axis. When you go over the x-axis, what you do is everywhere you see a y in your equation, you convert it to a negative y. And vice versa over y-axis. Everywhere you see an x, you put negative x. And we started talking about a different kind of reflection, one where you take everywhere you see a y, it becomes an x, and everywhere you see an x, it becomes a y. So what this did is it took our normal axes, y, x, negative y, negative x, and it turned them into, it flip-flops them kind of, where the y, positive y becomes positive x becomes positive y. Same thing over here. Negative x becomes negative y, and negative y becomes negative x. So the previous ones, we flipped over the x-axis. So we spun our paper like this. Then we spun our paper like this. But now we're spinning our paper like this. So what I want to know is, what is the axis that we are spinning this over? Where we ended off last time. That green line, what is it? What's the function for it? So what is the general equation for any kind of line? General form. Y equals what? Come on, y'all. Y equals what? General equation of a line. Should be second nature at this point. Y equals mx plus b. Okay, so let's see if we can figure out what is the equation of this green line. So we're going to need to figure out the slope and the y-intercept. The easy one is the y-intercept. What is the y-intercept of this graph?
Which one?
What is the y-intercept of the green line on this graph?
0.
0. So plus 0 just becomes nothing. And what is the slope of this graph? So this graph is, in order to flip this x directly onto this y, and this y directly onto this x, that means that this line has to be the same distance from here as it is from here. Meaning if you go out 5 and you flip it, that means that you're going up 5. So what is the slope that goes out the same amount as it goes up?
1.
1. So we don't write the 1. The equation of this line is y equals x. So this first one is if you're flipping the graph over the x-axis, mirroring it over the x-axis. The second one is if you're mirroring it over the y-axis. And the last one is if you are mirroring it over the y equals x axis. This is a special kind of reflection. Did you have a question? Nope. Okay. So this is a special kind of reflection. And it has a special kind of property. It is actually what's known as a inverse of a function. So that's one of the things that we are going to talk a little bit more about when we're done with these transformations. But I like to put it in here because it fits nicely. But if you need to mirror it over a diagonal line like that, all you do is you switch the x's and the y's. Okay. So everything's good. So now we're going to start with the new family, the final family of transformations. And these are called non-rigid transformations. All right. So in non-rigid transformations, what does, I guess first, what does rigid mean? If something is rigid.
It's not like straight.
It could be straight.
Oh.
Let's see. Another, it's not, I don't think, directly related, but if you're talking about water that's really cold, you would say that it's frigid water. What does frigid mean?
Cold.
Not just cold, really cold, so much so that the water is probably not water anymore. It's what?
Ice.
Ice, yeah. So the water has hardened into ice. This is what basically frigid means. So if something is rigid, that means it is hard and it doesn't change its shape. And these are the kinds of transformations we've done so far. Are transformations where we moved it or we flip-flopped it, but we didn't actually change its shape. So now we're going to get into transformations where we do change the shape. All right. So let's see. These are in two basic categories. Stretches and funky looking R, and shrinks or squishes, depending on what you create for either, but here we go. So the idea here is we are going to take a graph and we are going to either stretch it, so we can stretch it to the side, or we can stretch it up, or we're going to squish it. So if we squish it, we're going to squeeze it in, or we're going to make it shorter. So let's start with our fundamental idea first. What did I say is going to be the kind of governing aspect to all of these transformations? What do I want you to think about when you do these transformations?
Did you say?
So it has to do with, I don't want you to think about actually touching the graph, the line itself. What do I want you to do?
Wait, say it again.
So draw a little thing up here. Let's just say that that's what we've got. All right, so we've got an equation, y equals x squared minus 4. So when doing these, I said I don't want you to think about actually moving the line. So earlier we talked about, okay, we're going to move the line up. What I want you to do is not move the line up, but what did we say to that all of these things are going to go basically run by the same idea?
I didn't catch it.
So it came from the analogy where I had two things side by side. And I said, you are looking at them, you see this. You look away, you see this. And I asked you which one moved. The thing is, you can't tell which one moved if you weren't watching. If there was nothing else, like if I wasn't here, because generally you tell which one moved by which one is different relative to where I am. So if they were right here, and this happened, the blue one moved because the red one is still over my shoulder. These stretches and squishes actually have a better, I think a more easily accessible version of this principle. Girls, or I guess we'll start with boys. It's generally less, I don't know, people get touchy when I bring this up. Guys, what is the best way, going out to the club or the bar or whatever, what is the best way to make yourself look strong or tall? I know this is a concept that everybody's familiar with, especially if you've ever been in middle school or high school. For girls, the joke is generally that what's the easiest way to make yourself look more attractive?
Makeup?
Even quicker than that.
Heels.
No. When you're going out,
Adjust.
you even easier than that. Y'all are gonna get some groans and roll your eyes when the answer comes out. So you're out with a group of people, right?
Right.
So what about the other people in your group will make you look better? Or the other way?
That's cheesy.
Perfume.
If everybody else is taller than you, you're going to look even shorter than you normally would by yourself. If everyone else is shorter than you, you're going to seem taller than you would otherwise. So the best way to make yourself pretty is have a bunch of friends that aren't maybe quite as pretty. Or the best way to make yourself seem athletic is to make yourself friends with people who aren't as athletic. And this is a basic principle of how human brains work, is we look at the thing that is most different from everything else in front of us. If we're at a rock concert, we can usually hear our friends, even if they aren't talking really loud, because that sound is different than all the sound around us. So this is the principle that all of this stuff kind of governs by, is we don't change the line itself. We do the opposite to the graph paper underneath it. So if you want to make the line taller, what you should actually do is make the graph paper smaller, because then the graph looks bigger compared to the graph paper. Vice versa. If you want to make the graph look squished, you don't actually make the graph smaller. What you do is you take the graph paper and you stretch it out. Here's what I mean. So if we want to make the graph skinnier, and let's say our graph looks like this. One way we can make the graph skinnier is if we make the graph paper wider. So if that is how it starts, and then we stretch it to where this is -1, this is -2, this is +1, this is +2. All we've done is changed basically the numbers on the line underneath on the graph paper. We haven't actually moved the line itself. So this, again, I know it sounds arbitrary, but it is easier to remember when it comes to actually doing this, because we do stretches and shrinks, or stretches and squishes, the same way. I'll show you what I mean. So if we want to shrink along the x-axis, by half. So this is kind of saying we want to make it half as wide. What we actually do is we make the x-axis twice as big. So what we do is everywhere we see an x in our equation, we transform it and we replace it with 2 times x. So this is what I mean by doing the opposite to the graph, to the variable. So think about what you want to do and do the opposite of that to the underlying graph paper, also known as the variables. So this is what we did here, because we wanted to make this graph look skinnier. So we changed the scale on the outside of it. We made the scale, it's actually a little bit more than twice as big, but we made the scale bigger. We wanted to make one of our friends look skinnier, so we made ourselves look bigger, vice versa. So let's do this a little bit more. All right. So somebody give me an example of something that they want to do to a graph. We'll start off, I guess I'll give you the graph y equals x squared minus 4. So somebody tell me if they want to shrink it or stretch it, in what direction, and by how much. So we've got shrink, stretch, in direction, and we will run through the math of how to actually do this. So somebody give me my stretching or squishing. Come on. You've got 2 options and neither one of them are wrong. Just say one.
What you mean, like for the first line, you're saying it could either shrink or stretch?
Yeah. Which one do we want to do?
Stretch.
Stretch. Okay. All right. And in what direction? What do we want to go? Do we want to stretch it in the y direction, which would be making it taller, or stretch it in the x direction, which would be making it wider? Again, 2 options, just pick one.
the y direction.
All right, so we're making it taller by a factor of how much? Twice as tall, 3 times as tall?
4.
4 times? Okay. All right, so we are stretching in the y direction by a factor of 4. So we're going to change the y variable because we're changing it in the y direction. And we are stretching it in the y direction, which means we're going to shrink the x direction. Okay. I'm sorry, not shrink the x direction, shrink the y axis. So everywhere we see a y, we're going to go to 1 over 4 times y. So plug that in. So we have 1 over 4 y equals x squared minus 4. And then you solve again for y. So y equals 4x squared minus 16. And that's it. That's all you do. So when you figure out your transformation, you apply it. So this is applying the transformation. Y goes to 1/4 of y. And then you plug it into your original equation and resolve for y equals something, or f of x equals whatever. So let's do an opposite one just to see. So we're going to do a shrink in x, and let's say by a factor of 3. So this means that, we'll do it in red. X, we are shrinking the graph. So that means we're going to make the graph paper bigger by a factor of 3. So everywhere we see an x, we're going to go to 3x. All right. Well, y equals 3x squared minus 4. So y equals 9x squared minus 4. And this is how you do all of the transformations. You figure out what you're applying, apply it, and then resolve and simplify for y, or f of x. So this is how we're going to be doing these going forward. What else? What else are we would we like to see? What else would we like to give me another one that if you guys want to go through it and talk about it.
At a factor of 10.
All right. So what are we going to do by a factor of 10? So let's even make it a little bit different. We're going to say skinnier by, we'll say 10 times skinnier. All right. So let's look at that word skinnier. If something is skinnier, what direction is it different? Is it different up and down or different left to right?
I think it's up and down.
If you lost some weight and became skinnier, would you get shorter?
Side to side.
When you're skinny, that generally means that you are less wide than if you were not skinny. So, not skinny, skinny. That's left to right. So, we're changing X. Now if something is skinnier, is it bigger or smaller? Is that a word we just don't like know? Skinny? What about thin? If something is thinner,
Repeat that.
what? What? I can't. So if something is skinnier, that means it's smaller. So X needs to be bigger. So it's 10X. Plug it in. Y equals 10X squared minus 4. Solve and simplify. Y equals 100X squared minus 4. So we're about to run out of time. But yeah, so they all run off of the same idea. Figure out what you want, what the question is saying to do to the graph, and do the opposite to the X or Y coordinate, depending on what kind of transformation it is. So that opposite thing is what comes in pretty important. So please keep it in mind.